Hello, differential equation students. We're going to be finding a Laplace transform. We're going to find the Laplace transform of t. I've got the formula up here. I know that right now we don't have a good idea of what this means yet. So this is where you have to just trust me for a while. We're going to be finding this extremely useful. When I'm finding the Laplace transform of t, that's going to be this improper integral from 0 to infinity of t times e to the negative st dt. Now I'm going to tell you right now, there are a lot of different ways that you could evaluate this. You could just go to Maple and plug it in. I'm not going to do that today because I want to emphasize integration by parts, because that's a technique that we need to be using for some of the work that we're going to see. So I'm going to go over here and I'm going to do some scratch. Just a reminder, here's our integration by parts formula. So I want to do that on this integral from 0, let's do the indefinite integral. So let's just focus on t e to the negative st dt. So my t is going to be my u, and my e to the negative st is going to be my v prime. And if v prime equals that, then I need the antiderivative, which will be negative 1 over s e to the negative st. All right, so that means I'm going to have u, which is t, times v, negative 1 over s e to the negative st, minus the integral of u prime, which is 1, yay, times v. That's minus 1 over s e to the negative st. So I'm getting minus t over s e to the negative st. I'm going to get a minus minus, that's going to create a plus, but when I anti-differentiate again, I forgot my dt, I'm going to get another minus 1 over s, so I'm going to have minus 1 over s squared e to the negative st. That was a whole bunch of scratch work, because now what I can do is I can go over here. Just as a reminder, when we are doing improper integrals, we're actually taking a limit. So this is the limit as b goes to infinity. Here's my antiderivative, minus t over s e to the minus st minus 1 over s squared e to the minus st, evaluated between b and 0. Cool, that's what we want to find. Let's move down here and evaluate that limit. So we're plugging in these values for t. So we've got minus b over s e to the negative sb minus 1 over s squared e to the negative sb minus what happens when I plug in 0 for t. Well, the first term disappears because I've got t right there, and the second term turns into minus 1 over s squared, because when I plug in 0, that term is 1. Now, we've got to figure out what's happening with these terms as b gets really, really large. Notice here that as b gets large, this gets large, but I have exponentials here. This is an exponential getting to a very small, I guess a very large negative power as b gets very, very large. Exponentials beat anything else. Well, I should say not anything else. Exponentials beat polynomials. So you could use some L'Hopital's rule here, or you could just remember that exponentials dominate polynomials. Regardless, while the b is growing, the exponential is shrinking, and the exponential will win that fight. So this term is heading towards 0. This term is even easier. The exponential is heading towards 0. So we've got a whole bunch of zeros, and finally a minus minus gives us a positive 1 over s squared. And we just found the Laplace transform. Now, you can clearly do a lot of this in Maple. My emphasis here today was to do some of it by hand to review integration by parts and to show you the definitions of what's going on.